Welcome back! In lab number 1, we explored the foundations of cloud computing with AWS, focusing on services like Amazon EC2, S3, CloudFormation, and Cloud9. We learned how to deploy and manage resources efficiently in the cloud, setting the stage for more advanced applications. Today, we're diving into lab number 2, where we tackle a common challenge faced by data scientists from across a lot of teams. So let's say, for example, you're working with large data sets stored in multiple CSVs. Multiple CSV files, of course, that are important to be stored in S3. Now, while S3 Select will help us perform individual queries on individual files, the task of querying multiple files and aggregating them is actually beyond S3's reach. Now, this brings us, of course, to Amazon Athena, which is a powerful interactive query service that lets us analyze data directly in Amazon S3 using your standard SQL. Now, Athena is serverless, so there's no infrastructure charge, and you pay only for the queries that you run. It is perfect for quickly running ad hoc queries against, large data sets that are stored in S3 using the data that were already stored in there, where there's no need for complex ETL. Now, this is actually a very practical use case because a lot of us may actually be collecting data periodically. So you may have data for January, February, March, April, and so on and so forth. And all of this, for example, in S3 Select, you may, if you want to find out items or query across all these different months, you won't be able to do so with S3 Select because you can only query a particular file. And this is actually the example that we will be using right now. So the very first thing that we need to do is actually to log in into our AWS account, and we go to S3. As I mentioned earlier, it's very important that your files are already in an S3 bucket. So let's say, for example, for this one, if I'm going to create a new one again, but I'm not going to click create because I already have one, it should be like this. So I'll create a bucket, and the bucket name should be yellow bucket for DE Lab 1. I will just use the standard options. I will not change anything else, and of course just go and create the bucket. After creating the bucket, so since I already have it here, please go into that bucket and create a folder. So that folder will be named yellow. Create a folder named yellow, and here we will upload our dataset. A little bit about our dataset. We will be using the NYC Taxi Limo or the NYC Yellow Taxi dataset, of course, from taxis in the New York, and they're named yellow because I believe that there are two types. There's a green and yellow taxi. So here in the data.world, I managed to compile every the monthly data. So it's actually very huge file. So there's a January file, February file, March file, and if you collect all of that, you have it, for example, here. So for my class, I will be giving this link, and they can proceed to download this into their local computer or upload it to the S3. So once done, please proceed to upload the data, all of the data here in the yellow folder inside the S3 bucket. So that is so important. Let me repeat that. You must have an S3 bucket with a folder named yellow. For this exercise, it can be any name, of course, but for our exercise and for you to follow follow me in my steps later, it should be named yellow for now. And in that yellow folder, please upload the individual files. There should be 12 files, and in here it'll be very important for us to get the link later for the yellow bucket. In my case, it took around 2 hours to upload all this, but it might just be my slow internet connection. So after uploading, you can now proceed with our next part of the task. And another thing, we need to create a bucket to store our queries for Athena, or those that we will be running in or through Athena, the Athena service. So for that, let's create the bucket and name it, let's say, bucket for Athena. Okay, and again, just the standard and default settings, and create the bucket. So once we have set up our buckets, it'll now be our turn to go to Athena. You can actually go to your console home and search Athena here. Or if you've recently used it, it will be in your recently accessed or recently viewed, but let's nonetheless search it. Okay, so once you're here with Athena, okay, you need to go to the query editor in this section over here in the left bar or the sidebar. So go to query editor, and we'll create first our database. So to create our database, so remember we have 12 different CSVs that we need to glue or combine together to create our queries later on. So to do that, first we need to create a database. So to create a database, we will be utilizing your standard SQL knowledge, which is simply just the command. So let's it will simply be the command create database, and let's call this database right now taxi data. Of course, we run that query, and once you've run it, you'll be able to see that you now have a taxi data database. To view that it has been successfully created, or to confirm that the database was actually created in the AWS Glue, we will be opening AWS Glue here the same way we've been searching the Amazon services through the search bar, and you'll see here in the databases that we already have the taxi data. The default here always it always gets created when you create a database with a name. Okay, so now we go back to Athena and perform our queries. So, okay. Now, in the Athena console, in the tables and view here, okay, in this section, we will create an S3 bucket data. All right, we will create a table from that S3 bucket data, and for now, enter here yellow, and let the description be table for the taxi data. Okay, and of course, let our database be the taxi data. And here for our S3, remember earlier we've created an S3 bucket, so we will now get the link to that folder. So to get to that link of the folder, open the other another console home, and go to your S3. Okay, so and go to your yellow bucket for DE Lab 1, which is what I've created. And here you can choose this folder here and copy the S3 URL. It's important that what you copy is the S3 URL, not the URL. Okay, it won't work with the normal URL. So then I'll input it here. This is the location of the input data set, and of course the file format is CSV. All right. Now, in the columns, of course, when you're creating a table, you need to specify the table. So we'll use this bulk add columns feature, which is of course very, very helpful. So I have it here already in my case, but maybe I can put a link as well for the text file. But to bulk add, simply just the format will be the column name and the type, comma, and of course you do that for the next column, and so on and so forth. And after that, we can immediately add all of that easily. Okay, so we were able to add all the columns all at once, and of course we will create the table. But after this, you will still have to run this. So this will be the query that has been formed, and if you okay, well, it's already been run, but that's why you have here the yellow table. Okay, all right. So now to confirm as well that this is likewise present in AWS Glue. So we go with AWS Glue as well. And once you go here, you'll be able to see here the tables, and you see now that yellow is present here. To view the data, okay, you can just click this and it will actually go to Athena as well, and the limit will be it will give you at least the first 10 rows. Now pay attention to how many query tabs you have here. The Athena can only run 10 queries simultaneously, or you should only have 10 tabs at this time of the video. So after we're done, for example, we were done with creating this, you can likewise clear this already, okay, and then because you've already managed to create the table anyway, and you can also close this as well because you already have the yellow table. And with that, we're done with task 1. In this task, you created an AWS Glue database and table by using the Athena query editor. You connected your Amazon S3 dataset to the table and defined the schema for the table by using the bulk add columns feature. And after you created the table, you learned how to preview the data by using the preview table feature, but in the AWS Glue. Now, with this particular setup, you can now query or do advanced SQL and query across multiple CSV files. This isn't possible with S3 alone. Alright, so now we go to task 2, which is optimizing Athena queries by using the buckets. When you work with large data sets that spread out across multiple files, such as the one that we have, where we have 12 different CSV files, all which are large in size, two major goals are, of course, to optimize query performance and to minimize its cost. Now, cost for Athena is based on usage, which is the amount of data that is scanned, and of course, the prices vary based on your region. So, three possible strategies that we can utilize to minimize the cost and improve the performance are, of course, number 1, to compress your data. Number 2, to bucketize your data, or bucketizing your data, meaning put it into different buckets. And number 3, to partition your data. Now, compressing your data, such as what we've done with Lab 1, of course, we will be using some of the open standards for file compression, such as the gzip or tar. Of course, compression results in a smaller size for the dataset when it's stored in Amazon S3. Now, here's an important thing or concept to learn as well. The cardinality of your data also affects how you should optimize your query. So, of course, cardinality refers to how unique the values of the columns are. So, for example, when you have a unique ID column, that column is considered to be to have high cardinality because it has a lot of entries, but none of it are repeating. But for example, you have a categorical column. That's a column that is considered to have low cardinality. For high cardinality with data, we store records in distinct buckets. Now, it's actually based upon a shared value in that specific field line. Okay, so that's one strategy to bucketize your data. It's the bucketization that we are talking about here isn't really the S3 buckets now. It's really just about you segregating or grouping your data into something that they have shared value in a specific field. So for this lab, for example, for data for a single month will be bucketized separately from the original data set, or maybe carved. Maybe that's the term that you might be familiar or more familiar with, which contains the data for, let's say, an entire year, right? So now this strategy will help, of course, to optimize the performance. We will also be doing partitioning. You can also use partitions to improve the performance of your query and reduce the cost. Now, Partitioning is a strategy used with low cardinality data, and later in the exercise I will be referring to which method we used. So for this task, we'll experiment with bucketizing the data to optimize Athena queries. So for this, we will create a table named Jan for January. So we go back to our query editor. So we now have a table here named yellow, and we have to create another table named January. Now, since in the same manner that what we've done earlier when we created the yellow table, we likewise need that data to be stored in S3 and also inside a folder, because what we will be getting, just a review, is the S3 link of that folder. So again, we go back to right now for the S3 here. So we go to our buckets and create in the same manner as we have created earlier for the yellow bucket, but now I have created a new one, which is yellow dash January dash DE lab 2, and I created another folder, January, with a capital J, and just placed there, it's the same data, but I place here the yellow underscore trip data underscore 2019-01 .csv, and this is of course the same file that we've just carved out from the database, or that the original database that we have uploaded into the yellow or yellow table. Now after this, so securing that you have this S3 bucket with the January folder and the January data, then we again go back to the bucket, open that bucket, and remember we need the S3 URL, not the URL, but the S3 URL of the folder. We copy that, and then of course we again create a new table. So create from S3 bucket data, and we'll name this Jan small j. All right, and maybe type here table for January 2019 data. And for the location of the input data set, this is where we will paste the S3 URL, which we have copied. And of course, the file format is CSV. It's very important to get this correctly. And of course, for the column, we will utilize again the bulk add column. And I guess we have this as well. The bulk add column, we just need to get the same columns file or text file that we have earlier. Same format. It follows the name of the column, then type of the data type of that column, comma for the next one, for the next column, and so on and so forth. We have to add it, of course, and of course create the table. Once we have done that and we see that it's a success, you'll see here the January table. Now, to test this in action, we will be querying both the January table and the yellow table for just the January data. We'll try to check which one's more optimal, but of course I think from how I'm setting up the question, you'll probably already know that it will be the January table, but it's still better to see it for ourselves, right? So the query that we will be using is this query. It's so please create another one here, or maybe since we're done with this one, maybe we can just select count. Oh, sorry, you have to delete this first. So after that, we finished querying it, and it took around 6.81 seconds to return 2,245,463 rows, right? 2 million rows. And we'll try this again, but instead of querying the yellow table, we'll query the Jan table that we have created. So for that, we'll type again this query, okay, but we will change this from yellow to just Jan, and of course because it's just the data for January, we don't need this condition. We just need to group by pickup, right? And let's run it again. And here you could see that instead of 6 seconds, we're able to get our query within 5 seconds. It's definitely faster, and of course you get charged with the data scanned, so this one is going to be your base as opposed to the other one where it was around well, more than 5 gigabytes, right? So now notice that there are some different numbers here. That's because for the yellow data set, okay, for the yellow data set, it contains more transactions that are supposedly for January recorded in the month of February, but that should be okay. Of course, barring that nuance, it should be the same. We're here to study anyway the optimal query performance. Okay, so for the next one, we need to also learn how to optimize our query by doing the partition. Alright, now this effectively finishes our task 2, where of course in this task you created a table for the January 2019 data, and of course you've learned how to optimize the query by using multiple buckets. It's more efficient than the faster when you query it in that way, of course, because the data being scanned is much less. Let's optimize Athena queries by using partitions. If you are interested in creating a field with low cardinality, which means that the field has few unique values, you would partition the data instead of using distinct buckets. Now, in some cases, your data will be partitioned by another process, but to find the most efficient approach, you will try to partition the data using the, let's say, pay type field in the specific query in the Athena. So, for example, in our taxi data set, the pay type field stores the type of payment by using the following codes. 1 is for credit card, 2 is for cash, 3 is for no charge, 4 is for dispute, 5 is for unknown, and 6 is for voided trip. Now, because the set of possible values is limited, pay type is an excellent column to use to create partitions. In this task, let us create a table as function to partition the data. We'll also specify a columnar storage format. Now, in our case, we can store data in Athena with the Apache Parquet or optimized row columnar or ORC formats. Columnar storage formats compress the data, which will further reduce the costs for your queries. So, to create a new table called taxi.creditcard that is partitioned from for the pay type equals 1, which is credit card, we run the following query in a new tab. So alright, so it took a while for that query to run. It ran around 24 seconds, but right now we now have the credit card table. Alright, so to test the efficiency of partitioning, we will query the non-partitioned data, and that is the yellow, the entire data set. And let's run the following query in a new tab. So the query will be... Alright, so after running this, we see that this is the amount that we have here. Please take note of that. And the runtime is around 2.4 seconds. Let's test the following query as well, but instead of querying it from the non-partitioned data, we will query the partitioned data. So it's quite of the same. Select sum total where pay type is, but instead from yellow, we change this to credit card. Okay. sorry, it's the credit card, yeah. And we group by pay type, okay, and then we run it. So we see that we are able to achieve the same number, so I told you to remember it, with just, with less time, with 1.8 seconds. Notice that the results of each query are the same, but the query on the partition data took significantly less time because it scanned less data. It's about this portion here, right? So remember that for Athena, you are charged for the amount of data scanned for each query. So since the last query scans less data, your cost is reduced. Alright, so in this task, you partition the dataset where the pay type field contained a specific value, right, which is pay type equals 1. Then you ran queries on non-partition and partition versions of the data and compare the results. Okay, so now we go to our next task, which is using Athena views. You might have noticed that Athena can create views. Creating and using views with data can help to simplify analysis because you can hide some of the complexity of the queries from the users. Of course, Athena supports running only one SQL statement at a time, but you can use the views to combine the data from the various tables. It's actually what we're going to do later. You can also use views to optimize query performance by experimenting with different ways to retrieve the data and then saving the best query as a view. Okay, so in this task, we will do the following. Create a view to calculate the total dollar value of taxi fares that were paid with a credit card. Create a view to calculate the total dollar value of fares that were paid with cash. Retrieve all records from each of these views and create a new view that joins the data from these two views. And of course, we would as well preview the results of the two joins. So you can open up a new tab or simply just maybe delete those that are not being used. As you know, we have a limit of 10 tabs that are opened for Athena at any given time. So let's type our code. Let's create a view. Okay, so this particular code that we wrote will create a view called as CC trips or credit card trips, and it will appear here. So for the tables we have created, we have 3, but for the views it will be here. So let's run that. Okay, so there was an error in this code. There shouldn't be a comma here. So now that we've run it, it's now available here. You can likewise preview this. Okay, so if you preview this, you'll see okay, there. So those that have paid credit cards through credit cards are divided into 3 vendors, 1, 2, and 4, and these are the amount. So to create another one for cash trips, of course, then maybe you can just copy this, and if you want, you can we'll create a new tab for that. Okay, new tab. Sorry, not that. We're not supposed to copy that. It's the other one. This one. Okay, and well, maybe you can just put it here. And instead of CC trip, we will call it cash trips. Right, a sum from or as cash total vendor, and the pay type is 2, of course. Okay, and we're going to run it. There, so we now created another view for cash trips, and to preview the view, okay, we can just see it here as well. So okay, from different vendors, 1, 2, and 4, these are the generated cash from those that have opted to pay cash. Okay, now let's maybe create a view to compare the pay across these vendors. Well, for both credit card and cash. So to do that, to combine the queries, or to create a new view from two existing view, let's create a new tab here, and okay, so let's run that. Alright, so we can view this table, or rather, sorry, not delete. We can preview the view for the compare pay, and there you see it. We managed to create a new or a fresh view from existing existing views that we have created earlier on. This essentially, well, overcomes the limit of Athena supporting just one SQL at a time, but if we manage to combine views, it's like simultaneously running those SQL queries, right? So we're pretty much done with task 4. In this task, you learned how to create views in Athena. You created 2 views to calculate the total revenue of taxi fares that were paid with credit card and paid with cash. And of course, you also learned how to use a view to join the data from 2 other views. Of course, the skills that you've learned with this task will help simplify the analysis of data by using Athena. So other departments may have less experience with AWS, so you or your team would like to simplify the process of using Athena for those departments to use. Now, in this lab, we will be focusing on creating the CloudFormation template to create a name query in the Athena. And of course, the template will not create the AWS Glue database or the tables or the data within it. This is a very important assumption. If you do deploy the named query to the other people, to other departments, it's important that they too have access to the data that they're going to have to query, and the database are likewise named similarly. So for example, in our case, we call it taxi data. Okay, so it's really just you have the same access to the same tables, and that is just that you will be deploying the query. So first, you want to experiment by building an example query and testing it by, of course, the other department's IAM user, right? So it's an assumption that we haven't been discussing, but they should be able to access that query, right? So that you'll be able to share the template with them. So let's say, for example, you want to write the following query, which gets all the fares that are more than $100. So okay, let's maybe remove this and just change this. If you run it, so after running the query, you get 185,221 rows that fit your query. Now, in this particular case, you now have determined that it works, okay? And we want to now navigate to our Cloud9 integrated development. Okay, our Cloud IDE for Cloud9. Okay, so in this particular case, I already have this instance, and let's take some time to open this. Okay. Okay, so once the Cloud9 instance has been activated, we'll create a new file where we will, because we're creating a CloudFormation template, and it's using, of course, like a text file, right? So I'll give you guys here the text file for this, but for now, assume that you have it and just copy this template. The AWS documentation as well for Athena will have this. So this is the Athena named query template, and so the name of this template would be fares over $1,000 US, and this is the query string. So remember, we've we tried this query earlier and we were successful. So the first thing before creating a cloud formation template is to test that this query worked, and you're really just deploying the string, right? So okay, now after this we'll save this file as save as, and let that file name be Athena query .cf cloudformation.yaml file. Okay, let's save it. Okay, so once it's saved, okay, it's now already a CloudFormation template. We'll validate that it's already been we want to validate that it's been saved, so we will run a terminal. So just click the plus here to add for the terminal, and type the following: AWS Cloud Formation validate template. Okay. All right, so we have a wrong. So we forgot the letter D here. All right. So if the template is validated, the following output should display, right? And if you receive an error that says YAML is not well formed, check the value of the name of the query and also the tabs and the spacing for each line. YAML documents require exact spacing, and the parser will continue to encounter the errors if the spacing doesn't match. Of course, for this particular lab, don't go to the next step until the template is validated. Now, if you're successful in validating it, let's now create the stack by running the following command. So the command will be AWS Cloud Formation. So we've really just validated the template earlier. We're now gonna create a stack. Okay, create stack. Okay, and then stack name. Okay, using the template, and query that. Okay. All right. So if the stack is validated, you'll see here the CloudFormation Amazon resource name, or the ARN, which you see here, the ARN, and it should display something like this in the output. Now, we've already discussed this last lab 1, but the CloudFormation creates stack command creates the stack and deploys it. If the validation passes and nothing causes the stack creation to roll back, then we are successful now and we can proceed with the next step. We can confirm our named query resource that the CloudFormation stack has created. So to do that, to confirm that, you can just type AWS Athena and then list the named queries. This is the ID associated with the name. The name query ID is a unique identifier in AWS for the query that, of course, you have created by using the CloudFormation stack. Now, we can copy the query ID, this one. Okay, copy this to a text editor, and of course, after we've copied this to retrieve the details of this named query, including the SQL statement that is associated with it, we can run the following AWS. All right, so the string name of that is the fares over $100 US, and the descriptions including the query string is now presented. Of course, if you want to save it as a bash variable, what you can do is, for example, well, let the variable be enqueue, and this is the query ID. Okay, and to verify that the name query ID was really stored in the bash variable enqueue, you could try echo and then $sign. There you have it. Okay, now we're essentially done. In task 5, we learned how to integrate an Athena named query into a CloudFormation template, and also learned how to validate and deploy a template to create a named query in the CloudFormation stack. But before we end this session, please ensure that the necessary AWS resources that you've turned on, particularly for the Cloud9 EC2, has been switched off or terminated. The term is terminated for the EC2 instance so that it won't incur any additional cost. I'll see you guys in the next lab session.